Now we know how to find the area under curves by computing that definite integral, but what if we want the area between curves? So maybe we have these two curves, they could go above or below the x-axis, and we want to know this area between them. Well, of course, the first thing we're going to do is the similar thing we did for finding the area under a curve. We're going to divide this up, and we've got these various rectangles. Let's look at this pink one here, and all of our little widths are going to be delta x, but what is the height of this rectangle going to be? We see that this is f of x right here, and then to get the rest of this I need g of x, except that g of x will give me a negative value, so I need the opposite of that. So if I took f of x and I subtracted g of x, if g of x was negative, essentially that will make me add the value there, and I will get this height of this rectangle. Now let's look over here at this last rectangle. What if g of x was above the x-axis? Well, if I took f of x, that would be this whole thing. That would be too much, but if I subtracted off g of x, if g of x was positive, oh, that's still going to give me the height of that rectangle. So that's going to work in either of those cases. So what we're going to do is take our little representative rectangle. Its width is going to be delta x, and its height is going to be the function at some x value on the ith interval for f of x minus g of x. And then if we take, this should be an n, if we take the limit as n approaches infinity, sum up this number of angles and let the number of triangles go to infinity, we have the integral. So the area bounded by the curves f of x, g of x, and the lines x equal a and x equal b, where f and g are continuous, and f of x is greater than or equal to g of x, would give us this integral. Now this is important because we need to know which function is above the other function, and it could be above or equal, and we would need to take the function that was above and subtract the function that was below so that we got the correct height for this. Now what if we had both functions always positive? We actually could take and we could integrate from a to b and find f of x dx, and that would give us all of this, and then we could integrate from a to b g of x dx, and that would give us this area here, and then we could subtract them, and that would leave us what we needed, the area between curves. And if we did that, we actually could combine these integrals, and we see that when we do that, we have nothing more than what we had just a minute ago when we said how we would find the area between curves. So this is going to work if it's entirely above the x-axis. It's going to work if f goes above and below and g goes above and below. The only requirement is f always needs to be greater than or equal to g. So we need to make sure that as we do this, they are using y of the top function, meaning the one that's greater, and y of the bottom function, and we need to make sure we have it correctly. So often we will draw a sketch or a picture so we can get a sense of what's going on with that. So let's see an example. Find the area of the region enclosed by the parabola y equal 2 minus x squared and the line y equal negative x. So we want to draw a sketch so we can see which curve is above, and we also want to see our points of intersection so that we'll be able to set this up. This first curve is a parabola that opens down that is shifted up 2. So I can go ahead and put this on here, and I know it crosses the x-axis at plus minus square root of 2 because I could put this equal to 0. And then y equal negative x. Well, y equal negative x is going to come along like this. And so what we are after is this area right here, and it would go from this point to this point. Well, what are those x values? Well, they're the places where the curves intersect, so we could simply set these equal to each other to figure out what those would need to be. So this is going to be equals negative x. So this is x squared minus x minus 2 equals 0, and this will factor x minus 2 x plus 1 equals 0. So they are going to intersect at x equal 2 and x equal negative 1. So that looks about right, negative 1 and at 2. So I can compute this. If I integrate from negative 1 to 2, and I need to take the function that is above, well, I can see that that's my parabola. So I'm going to take 2 minus x squared and subtract from that the function that's below, and that's the negative x, and then dx. Let's go ahead and kind of simplify this, and then we'll do the antiderivative, and then we'll do the evaluation. So I'm going to go ahead and list the negative x squared, and this is going to be plus x plus 2 dx. And we can do the antiderivative. That's going to be negative x to the third over 3 plus x squared over 2 plus 2x. And that's evaluated from negative 1 to 2. And so we have negative 8 thirds plus 2 plus 4 minus, this would be 1/3, and this would be plus 1/2, and putting a negative 1 in here, minus 2. So it looks like when we combine those we get 9/2. Now something we have to be careful about. What if f of x is not always greater than or equal to g of x? Then this is not going to work. We would need to look at this and split this up. So if I was looking at something where f of x was above, I could do the integral for this first piece and have f of x minus g of x dx, but then I would actually need to integrate from x values from here to here and do g of x minus f of x, and then I could integrate the last piece from this x value to b, and again f of x minus g of x. So it's important, we're going to have to be careful that we know that f of x is greater than or equal to g of x, or the first function, so function on top minus function on bottom. We're going to look at how we may change the integral, and let me show you what I mean. So we're going to find the area of the region in the first quadrant that's bounded above by y equals square root of x, and below by the x-axis and the line y equal x minus 2. So here we have a picture. Here is our square root of x graph in blue, and then we have our line y equal x minus 2 in yellow, and then we're interested in this part that's bounded below by the x-axis. So here is our region, but the thing we have to be careful about is as we're looking at our little rectangles here in this area for a, our lower function is y equals 0. This line continues down here, but we don't have this part of the area, so we cannot just do f of x minus g of x over this entire interval. So we're going to need to divide it up into two pieces. We are going to integrate from 0 to 2, and when we do that, the upper function is square root of x and the lower function is 0. So we don't need to put that, it's minus 0, and that's just like what we're used to doing when we get the area under the curve. Then we would need to add to that, and then we could integrate from 2 to 4, and the upper function is square root of x minus the lower function is x minus 2. And we would need to be able to sum those two together then to get that total. Now that works, but it involves splitting that up into two pieces and working two different integrals. So there is actually another option, and that option is, what if we made the rectangles going the other way and we expressed x as a function of y, and we had a little thickness delta y, and then we integrated this thing with respect to y. We could do that, and then we wouldn't have to deal with two different pieces, because we essentially, if we needed to find this, we would figure out what the x value was, x as a function of y for the whole thing, then subtract off the x as a function of y for this left-hand one. So we have the right-hand function minus the left-hand function, and that doesn't change anywhere that we pick here. This yellow is always on the right and the blue is on the left, so we could actually evaluate that in one integral instead of two. So the idea, we can make the rectangles go the other direction, and we can write x as a function of y, and if we needed to know how wide this rectangle was, it's going to be f of y minus g of y, because g of y would be negative here, and if you subtract a negative, of course that's going to make it positive, and so we would get that. If it was all entirely to the right of the y-axis, we're still going to be good, because if we had f of y and we subtract g of y, we would be left with the width of this rectangle just like we wanted it. And this one is just showing something similar where we were always positive versus here we could be above or below the x-axis. And either way, you can see that we are still going to get the correct values we needed for this width. So let's look at doing that, and we are going to be setting this up with the variables roles actually reversed then. We are going to look at the little width being delta y, and we are going to look at this, well, I guess that's a little change in height the way we have it drawn here, and then our width is going to be our right hand function minus our left hand function. And now when we integrate, we've got to look at values of y. We're integrating with respect to y, and our limits of integration would go from c to d. And instead of top and bottom function, it is the right hand function minus the left hand function. So let's try this. Find the area of the region bounded by the graphs y equals x cubed, y equals x plus 6, and the x-axis. And we could graph y equals x cubed. We know what a cubic looks like, and this is just a line whose y-intercept is 6, whose slope is 1. So here is the graph. Now, if we tried to do it like this, you can see that we could make these rectangles, but we have that same issue of anything to the left of 0. We have the upper function being y plus 6, and the lower function is y equals 0. But anything to the right of 0, the upper function is still y plus 6, but the lower function is x cubed. So we can do this in two integrals. We could go from -6 to 0 of the upper function x plus 6 minus the lower function, and then we could do from 0 to 2 the upper function x plus 6 minus the lower function, which is now x cubed. And this would work, but it would involve computing two integrals. So let's look at this and let's interchange x and y. Let's express x as a function of y, and let's make our rectangles go the other way. And you can see if we did that, we would only have one integral to compute, because the x cubed here, we're going to express it x as a function of y, but it's always going to be on the right, and this graph is always going to be on the left. So here's what our picture would look like with our rectangles going the other way, and we need to take these functions and solve them for x. So x would be y to the 1/3, because we would just simply cube root both sides to get x alone, and here to get x alone we just move the 6 over, so it would be y minus 6. Now we can see that these rectangles would be this y to the 1/3, the x value here, minus the quantity y minus 6, which is the x value over here. And since this is negative in this particular case, when we subtract that negative, it will make it positive, so it will add these. So let's go ahead and compute this. We are going to have the integral. Now we need to look at what y needs to go between. And so we are going to start with y equals 0, and we are going to go up to this point of intersection, y equals 8. And again, if we did not have that point of intersection, we could set these functions equal to each other to find that point of intersection. Now we're going to take the right function, which is y to the 1/3, and subtract the left function, which is y minus 6, and then we are integrating with respect to y. So we need to think of the power rule in reverse. So that would have been one higher power, but we need the reciprocal of that power. So that power out in front, those that cancel, decrease the power by 1, would look just like that. And then we'd have minus y squared over 2 for this piece. Distributing here, that would make that a plus 6. So that's going to be plus 6y. And then we would need to evaluate that from 0 to 8. So we have 3/4. I'm going to go ahead and put this in radical form. It's the cube root of 8 to the 4th, minus, putting an 8 in here, 64 over 2, so that's going to be 32. Putting an 8 in here, that's going to be plus 48, and the lower limit, evaluating that, they will all be 0. We can go ahead and do the cube root first and get 2. 2 to the 4th is 16. Cancel with the 4 there, so I get 4 times 3, so I've got 12. And then minus 32 and plus 48. And so finally it looks like I have 28. So we found that area by computing just one integral, because we chose to make our rectangles going horizontally here.